Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are starting to look at aldehydes and ketones. Aldehydes, if you remember, are molecules consisting of the carbonyl group, that is the C double bond O, carbonyl group. Off of the carbonyl, you have some R group, which is hydrogen, alkyl, or aryl, and the other group must be a hydrogen atom. Ketones, on the other hand, consist of the carbonyl group, in which there are two carbons attached to the carbonyl, no hydrogens attached to C double bond O. The carbons can be alkyl or aryl, and the RR prime designation indicates that they necessarily need not be the same. Now, aldehydes and ketones differ only in that the aldehyde must have at least one hydrogen bound to the carbonyl. Let's take a look at the nomenclature of these molecules. IUPAC nomenclature, the molecules are named as alkanes in which the A ending is dropped and replaced with Al. So two carbons, if you remember, a two-carbon alkane is an ethane. But if you make a two-carbon aldehyde, the ethane E ending is dropped, and this becomes ethanal. Now, in order to be an aldehyde, it is required that you be at the end of a carbon chain, because to be an aldehyde, you must have an H off the carbon, the C double bond O. If the C double bond O appears in the middle of a long chain, it is a ketone. Hence, aldehydes will always be 1. Hence, it is appropriate to say ethan 1-al. That's perfectly fine. But in order to be the aldehyde, you must be 1. And hence, it's equally appropriate just to say ethanal. Substituents are localized by numbering from the carbonyl. Carbonyl is a fairly high functional group. If you remember our ranking of functional groups, aldehyde is one of the highest. Only a few things are higher than aldehyde. And so if there's just an aldehyde and a simple side chain, the aldehyde is usually the highest priority, and so it gets the root, and you end up with Al as the ending. So there's 3 carbons. This is propane and propanal. And if we had an iodine here, that's located at carbon 2. Hence, this would be a 2-iodo propanal. Or you could say 2-iodo propan 1-al. That would be perfectly fine as well. All right. Likewise, there are some functional groups that appear in the root with aldehyde. If, for example, I have an alkene, this is named as a butene-al, and the alkene occurs at carbon 2, so this is a but-2-ene. Certainly appropriate to say 1-al, or just equally but-2-ene, and then al. Notice the silent E is dropped beside the vowel. In other words, you don't have a buteneal, a neal, it's just a nal ending, and so that E is dropped. Okay, how are ketones named? Well, ketones, the E ending is dropped and replaced with -one. And so cyclohexane, if it has a double bond O of it, becomes cyclohexanone. Notice we didn't have to say 1 in this case, because wherever the double bond O is located on a ring, that's where you start numbering. So no matter where I draw it, it's 1 cyclohexanone. So in this case, it's just cyclohexanone. You can put the 1 in, and if you're in doubt, always put the numbering in, in which case it would be cyclohexane 1-one. Now there are cases in ketones where you must put numbering in because you could get different numbers. Butanone, however, is one case where you don't have to. You can just say butanone. Wait a second, isn't that 2-butanone or butan-2-one? Saying butan-2-one is perfectly correct. There's no problem saying butan-2-one. But why can you drop it? Well, notice you can't have 1-butanone. 1-butanone would put it on the end, and that would make an aldehyde. If I move the C double bond O over here, I just number from the other end, and it would be a 2-butanone again. So 2 is the only option for a ketone. It isn't until you get to very long chains, say like this guy, that you absolutely must put the numbering in. Five carbons is a pentane. Drop the E, add one. That's pentanone. This is pentan-3-one. You can say 3-pentanone. It is just more accepted to insert it right beside the functional group suffix. Now, pentan-3-one. Why can't I drop the 3 and just say pentanone? Because if the C double bond O was here, or here, here, or here, if you move the C double bond O, you'd have 2-pentanone, and that's a ketone and impossibility. So to distinguish between it, you need the numbers. Again, as in the case of aldehydes, the root can have other functional groups such as aldehydes, as ketones. So you can have other functional groups with a ketone, such as an alkene. If I was to number this, I'd go 1, 2, 3, 4, 5, 6. This is a hexane. With an alkene, it's a hexene. We have a hex, 3-ene, and now we've got 2 ones, a 2,5-dione. Now I just want to make a note, what if you just had CH2s here? Notice that you don't contract to hexa. It isn't a hexadione. It's a full root, hexane, 2,5-dione. Only enes and ynes get contracted to hexa. That is, if we had 2 enes, this would be a hexa 2,5-diene. If we put enes at the 2 and the 5 position. Well, actually, that would be a 1,4. Yep. Which would be a better numbering system. But the point is, use the full root name hexane for diones, diols, everything else. Only enes, ynes get contracted to hexadione, hexadiene. All right. What about common nomenclature? Well, for aldehydes, we have several common names we need to understand. So for aldehydes, I can write an IUPAC name, and I can write down a common name. The IUPAC name, of course, for this molecule is methanal. You could say 1-methanal, but methane only has 1 carbon, and to be an aldehyde, it's got to be at the end anyway, so methanal. The common name for this molecule is formaldehyde. Formaldehyde. If we make the carbon chain a little longer, we get a C double bond O here. We now have 2 carbon chain. That becomes an ethanol under IUPAC, which is an acetaldehyde. Three carbons. Is a propanol. Under IUPAC nomenclature. Common name for propanol is propionaldehyde. 4 carbon chain. With an aldehyde at the end, so butanal. And a butanal becomes, under common nomenclature, butyr aldehyde. All one word. Butyraldehyde. And lastly, there are instances where IUPAC methodology of nomenclature has given way to accepting the common name. In this case, the common name, benzaldehyde, has been adopted by IUPAC. And the common name, benzaldehyde, is also the IUPAC name. Now, I say that the IUPAC methodology for nomenclature has been adjusted. What is the way of naming this if you followed normal nomenclature rules? Well, for aldehydes off rings, you name the full ring and you call it a carbaldehyde. So if you followed normal nomenclature rules, this molecule would have been called benzene carbaldehyde. You'll notice that for other rings, that this is the case. But let's take a look at some other scenarios. Benzene carbaldehyde is typically not used. Benzaldehyde normally is. Okay, so what we're going to do now is we're going to look at some common nomenclature for ketones. We've done the aldehydes, let's look at some ketones. Well, the simplest ketone, of course, is CH3. CH3. That is the molecule. Propanone. Now, if I counted the carbon, I would say propan-2-one, but the carbonyl has to be there, so propanone is fine. What's the common name for propanone? That's right, it has a special name called acetone. Acetone. How about butanone? Likewise, butanone, you can say 2-butanone. You don't have to, because to be a butanone, you have to be 2-butanone. When there is no special name like acetone, a common method of common nomenclature that was accepted was to use the word ketone for the carbonyl group and separate words for the alkyl group. So we have a methyl on one side of the carbonyl, we have an ethyl, and so we say methyl-ethyl ketone. Typically, the methyl, smaller group methyl, is listed first in common nomenclature. If you have two identical groups, such as 3,3-pentanone, or pentan, -3-one, you simply say diethyl ketone. So it looks like you name the alkyl groups and you use two words. In some instances, you have complicated alkyl groups off your ketone. In such a case as this, let's make some space here. I'll have to write the names a little lower. You have 2,2,6 trimethyl hexane 3-one. Well, the common name for this, on the left-hand side here, we have an isobutyl. On the right-hand side, we have a tert-butyl. So the common name is isobutyl, tert-butyl, ketone. Now, in some cases, common nomenclature has been adopted by IUPAC. The IUPAC name for methylphenylketone is acetophenone. Acetophenone or acetophenone. And as I stated, its common name is methylphenylketone. And you say, well, didn't you just call acetophenone the common name? Some molecules have more than one designation that was commonly used, and some of those become the IUPAC designation. And of course, there's the ketone, which has two phenyl rings off of it. And that is the molecule benzophenone. Benzophenone. Now, benzophenone would be called diphenyl ketone. Diphenylketone. Now, in common nomenclature, when we have a substituent off the chain, we don't localize the substituent with numbers. For example, if I have a butyraldehyde or a butanal, actually let's put it here. If I was giving the IUPAC name, and say there was a bromine here, I would write down, number from the aldehyde, 1, 2, 3, I would write down 3-bromobutanal. 3-bromobutanal. However, when using common nomenclature, I localize the functional group. This is my aldehyde group. right there. That's my aldehyde group. The carbon attached to directly to the aldehyde is called the alpha carbon. The carbon attached next to the alpha is the beta. After that, we have gamma and delta, and so on. And so in common nomenclature of aldehydes, you often localize or designate the location of the substituent by using Greek letters. In this case, we have beta bromo butyraldehyde. Now, because of this, this is called a beta bromoaldehyde. The nature of the molecule is referred to as a beta bromoaldehyde. Let's try this molecule. Let's name it by IUPAC, then we'll name it common nomenclature, and then we'll see where that common name comes from and designate the functional group much like we did here. This is a functional group designation. So the IUPAC name, this is a 1, 2, 3, 4, 5. It's a pentane with 2 ketones, so it's pentane dione, and the ketones are at 2, 3, 4. This is a pentan. Two, 4 dione. Okay. Now the common name, interestingly enough, is based on this molecule. What's the common name for this one? Well, clearly this molecule's acetone. But you notice this molecule above looks like it has this group attached to an acetone. We just drop the H and make that a CH2. So we have an acetone, and this is like our substituent. What kind of substituent is this? This is an acetyl, sometime given the prefix acetol. So you'll see acetol, acetol. So this is referred to as acetyl acetone or acetyl acetone. As the common name. Now, what kind of molecule is it? Well, we use Greek letters here, right? It's a ketone. It's actually a diketone. But we can indicate the relative position of the ketones to each other by fixing one ketone and saying this is the alpha carbon and that's the beta carbon. And so these are beta. This is an example of a beta diketone. Now this type of terminology you'll hear in lectures. I'll often say a beta diketone, a beta bromoaldehyde, or an alpha beta unsaturated aldehyde or ketone. Let's take a look at one of those. Here's an aldehyde with an alkene in it. In other words, a 2-butene or a but-2-ene-al. But-2-ene-al. Okay. So I have an aldehyde with an ene at carbon 2. This molecule has a special name that you need to know as a common name. Memorize. Croton. Croton aldehyde. Now, localize the aldehyde group. There it is. Find the alpha, beta, gamma, delta. Where's the double bond? The double bond is between the alpha and beta carbons. In double bonds, we usually use the word unsaturated. So we often say this is an alpha, beta, unsaturated aldehyde. An alpha-beta unsaturated aldehyde. We can also describe ketones this way. Name this molecule by IUPAC methods. We have a 2, 1, 2, 3, 4, 5. So we have a pentane with an O is pentanone, a pentenone. The ene is at carbon 3. Pent 3 ene 2. Gotta put the 2 in because the one could come someplace else. 2 one. All right. What's the common name? Well, common names are named by calling them alkyls around a ketone. Here's a ketone and this is methyl. Where does the word methyl come from? Well, methyl comes from a single carbon, which is a methane, right? We drop the ane and add YL. If you have a substituent like this, which is derived from a propene, we drop the E on ene and add YL, and this becomes a propenyl. And so the common name for this molecule would be methyl space propenyl ketone. No problems. Again, here's the keto group. Okay. And you know, you have an alpha carbon here, you have an alpha carbon here, you have a beta carbon here. Notice this guy is an alpha beta, oops, unsaturated ketone. So methylpropenyl ketone is an example of an alpha beta unsaturated ketone. So don't be thrown by these designations. One last group designation is referring to something as an omega substituent ketone or aldehyde. For example, if I have a bromine at the end of a long chain, I'm not naming this molecule, but I can designate this as an omega bromo ketone. Why omega? Omega is the last letter of the Greek alphabet. It comes at the end. And so when you say omega, you're saying that the bromine is at the end of the longest chain on the ketone. Okay? It would be equally appropriate to designate alpha, beta, gamma, delta, a delta bromoketone. Omega says it's at the end. Delta says it's 4 carbons further out beyond the carbonyl. The last thing I want to look at in regards to nomenclature is the IUPAC nomenclature of aldehyde groups off rings. For example, you might have a cyclopropane attached to an aldehyde group, or a cyclobutane. You can go to cyclopentane. Cyclohexane, and so on. We'll just do these. All of these are named as carbaldehydes, giving the ring structure its full alkane name. So this would be cyclo, and this is IUPAC. cyclopropane carbaldehyde. Likewise, the next one is cyclobutane. All one word, no space. Carbaldehyde. And then cyclopentane. Carbaldehyde. And this one's cyclohexane. If we kept going, we'd have cycloheptane, cyclooctane, all carbaldehyde. It is only used when you only have a C double bond OH directly attached. If the chain was longer, then it would be named by ethanal with a substituent of cyclohexyl or something to that effect. So the term carbaldehyde means a C double bond OH directly attached to the ring. Okay, well that's a quick summary of the nomenclature of aldehydes and ketones. One of the things we want to look at before we leave, though, are physical properties of aldehydes and ketones. Now, whether I draw an aldehyde or ketone, they both have one common feature, and that is derived from the carbonyl group. Now, the presence of the carbonyl group leads to several related features. For example, they have a polar pi bond. There's a delta minus and a delta plus here. Equally, there's lone pairs on the oxygen, and they both possess the carbonyl pi bond. The dipole is approximately 2.85 to pi. Now, because of the dipole, acetone molecules will interact with each other through dipole-dipole interactions. However, there is no hydrogen off an electronegative atom, such as oxygen, so there's no hydrogen bonding between acetone molecules. So if I was to create a trend and compare several structurally similar molecules, such as isobutane, acetone, and isopropyl alcohol, I would see a trend in boiling points, such as minus 12 degrees Celsius for isobutane, 56 degrees Celsius for acetone, and 82.5 degrees Celsius for isopropyl alcohol. Why the difference? Well, the isobutane, of course, only has van der Waals forces. Van der Waals forces. The weakest force, the weakest intermolecular force, and as such as the lowest boiling point. Acetone has our dipole-dipole forces. A stronger intermolecular force, interaction between the carbonyl dipoles of different molecules. Isopropyl alcohol is the strongest of the dipole-dipole forces, so strong it's given its own name, a bit of a misnomer. Hydrogen bonding, not a bond, really an intermolecular force. Hydrogen bonding. And that accounts for the higher boiling point. Now, while the carbonyl compounds do not have hydrogen bonding in pure form so that they can have the stronger intermolecular force of interaction, they are often very water soluble because the lone pairs on the oxygen allow molecules such as water that have hydrogen bonding to hydrogen bond to the acetone through their hydrogen. So you could have a water molecule here where the delta plus on the H would be attracted to the lone pairs, and water could hydrogen bond to acetone. So acetone is infinitely soluble. Once you get to longer carbon chain ketones, such as butanone, the solubility starts dropping off. And as you go to longer, you get less and less solubility in water. Okay? But low molecular weight aldehydes and ketones tend to be very water soluble. Okay, well that's it for the introduction to aldehydes and ketones. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.